Imagine a world where the rules of reality bend, crack, and then completely break. A world where a particle doesn't just do two things at once. It follows two different sets of instructions at the same time. Welcome to the new, deeply unsettling frontier of quantum physics. For decades, physicists have used a test called Leggett-Gauge inequality, or LGI, to check whether a system behaves classically. Classical systems, like planets, apples, or your phone, always respect this limit. Quantum systems, on the other hand, violate it. That's how we know they're truly quantum. But even the quantum world has a limit, a ceiling called the temporal Cyrelson's bound, or TTB. It tells us how weird quantum mechanics is allowed to get, until now. A team led by Arijit Chatterjee at the Indian Institute of Science Education and Research asked a simple but radical question: what if there's an even deeper level of quantum weirdness we haven't accessed yet? Their idea: make a quantum particle evolve under two different motions simultaneously, not an average of the two, not switching between them, but a superposition of unitaries. One particle obeying two evolution laws at once. This is not supposed to be possible in the classical world, and even in quantum mechanics, no one knew if it could break fundamental limits. To test this, the team used an NMR machine, the same kind of tech used in MRI scanners, to manipulate a single qubit inside a molecule. They built a precise quantum circuit, adding an extra helper qubit to force the system into this superposed motion. Then they measured the LGI violation, and what they found shattered expectations. The system didn't just violate the classical limit, it blew past the temporal Cyrilson bound itself. They broke a boundary previously believed to be absolute. Even stranger, the more strongly they mixed the two motions, the stronger the LGI violation became. The universe got weirder in a controlled, tunable way. And perhaps the most important discovery: this exotic motion actually protected the quantum state from environmental noise. In other words, the superposition of unitaries makes fragile quantum states more stable. The very thing that usually destroys quantum behavior, decoherence, is pushed back. For quantum computing, that's huge. If this effect can be scaled, we could develop quantum processors that stay coherent for much longer. Machines that use exotic superposed motions to resist environmental noise, and entirely new ways to encode and manipulate quantum information. This research doesn't just push the boundaries of quantum mechanics. It suggests those boundaries were never real to begin with. So, what does this mean for our understanding of the universe? It means we've only been seeing the surface of quantum reality. And that deeper down, the rules get stranger, sharper, and far more powerful. The quantum world is not just weird, it may be far weirder than we ever imagined. Thanks for watching, and if you enjoy exploring the frontiers of science, be sure to subscribe.